Well, I'll say that. Yeah, that's all right. Wow. Okay, let's do a sound check. Can everyone hear me on the other side? Are people on Zoom?
Yep.
Great, we can hear you. Me? All right, so maybe we should start class. I hope everyone had a good weekend. So what I like to do is I like to sort of remind you about the midterms. So the midterms will be next week. The first sort of group will come in on Wednesday. I'll send an email out to everybody about instructions. So let me just break this out. So the midterms will be midterm 1. So one group will come in Wednesday, the 30th. So maybe I'll call it this group 1. The other group will come in Friday. I believe that's October 2nd. And that'll be group 2. Okay. So I'll send out an email probably this week in terms of which group you're going to actually be in. Also, I will need you to bring your IDs for the midterm. So bring your student ID with a photo, please. So you should bring IDs. And then because I haven't actually seen a lot of people face to face, I need to actually check. And then secondly, calculators are allowed. And then what you'll have to do is you'll have to show your work on your test. Okay, so to get full credit for answers, you just can't put down like the answer that, just an answer itself. You have to justify your answers and how you actually got there. So. Okay, are there any questions on this? No? Okay, good. So let's back up a little bit. So last time we were talking about the idea of inverses. All right, so we start out with the following framework. So let A, B, and n by n matrix. So we're all only dealing with square matrices here. Okay? So number of rows and number of columns are the same. So A has an inverse if there exists B, which is also an n by n matrix, such that when I take the product of A times B, I get the identity and vice versa. B times A is the identity. And recall what the identity matrix was. It's just the matrix with ones down the diagonal and zeros everywhere else. So this is the n by n identity matrix. Okay. Now, last time what we saw was if a matrix does have an inverse, then the inverse is unique. So the inverse, if it exists, is unique. So when A does have an inverse, we say B is equal to A minus 1. Okay. All right. And another thing that we sort of defined was that if A has an inverse, then A is what's called non-singular. So invertible matrices are non-singular. So if A does not have an inverse, then A is called singular. Okay. All right. Any questions on this sort of recap that, from last time? Okay. So let's move on. So we have the following. So in the 1-by-1 case, we looked at invertible matrices. So in the 1-by-1 case, let's call this matrix A. So this is invertible if and only if A is not 0. Okay, so we can actually find an inverse, namely A minus 1, if and only if A is not equal to 0. So now we go to the 2-by-2 case. And so let me just write out a 2-by-2 matrix. This is A, B, C, and D here. And as long, oh, is there a question? Okay, so as long as AD minus BC is not equal to 0, i.e. the determinant is not 0, then this matrix is invertible. So A, first of all, is invertible. In this case, if and only if, and I'll just write this as a determinant. Someone mentioned it last time. AD minus BC is not equal to 0. Okay. And if A is invertible, then we actually have a formula for the inverse. So A minus 1 is 1 over AD minus BC. And then what you do is you switch the A and the D. And then you negate B and C. Okay, so if you say it to yourself like 3 times, you'll remember the formula. Okay, any questions on this so far? All right, so let's do some examples. Okay, so I want you to find the inverse of following matrix. A equals 3 minus 7 and minus 6, 13. Okay, so first of all, to find the inverse, we're just going to use the formula right above the example. And so let's calculate the determinant first. That's what AD minus BC. So what is A here? A is 3. B is 13. B is minus 7. And C is minus 6. Okay, is everyone all right with that so far? Okay, so we have what? 39 minus 42, which is minus 3. Okay, so the determinant is minus 3, clearly not equal to 0. So that means that this matrix has an inverse. And so now what we can do is we can write the formula for the inverse. So A inverse is 1 over minus 3. That's AD minus BC. All right, so who could tell me what the first entry is going to be? Anyone?
13.
13, good. What about the next entry over here, next to the 13 to the right?
7.
Okay, so you negate this one, so it's 7. That's right. Next entry?
6.
6, good. And the final entry?
3.
Okay, so I'll just write it out in a little bit nicer form. 1/3, 13, 7, 6, 3. Maybe I should clean it up a little bit. Okay. All right, any questions on this? All right, let's move on. So now you might ask yourself, why are inverses important? What are they good for? So it turns out that if you have a system of equations, let's say you have system of n equations and n unknowns, and you want to solve the equation. If you know the inverse, then it's easy to solve the equation. So let me indicate why that's true. So this is called YR inverses important. So let's say I have a system of equations. So I have AX equals B, and this is an n by n system of equations. Okay, so it's kind of a special case. So you have n equations and n unknowns. Okay? Now suppose A is invertible. Okay? So we can take this equation and, well, what's the thing we normally do? We just take the inverse and we apply it to both sides. So then we have A inverse AX is equal to A inverse times B. Okay? I think we've done this trick like several times. And now what we do is we associate A and A together, A inverse and A, and that's X is equal to A inverse B. Okay, so we know that A inverse A is the identity. Okay, so we can plug that in. And so we get X, the solution, is equal to A inverse B. Okay. So what is the conclusion here? So suppose A is invertible, then how many solutions do we have for this system of equations?
One.
One. Right? So this shows that the system of equations has a unique solution. So in this case, the system of equations has a unique solution. Namely, X equals A inverse B. Okay, so if you have an invertible matrix, then any system of equations you have involving AX equals B will have a unique solution. Okay, any questions on this? All right, so we'll do another example. All right, so here's the example. So solve the following system of equations. Okay, so I have 3x minus 7y is equal to 10. And minus 6x plus 13y is equal to 2. Okay. Now, we know how to do this using Gaussian elimination. And that turns out to be, generally speaking, the most efficient way to do things. Right? But in this problem, let's solve the system of equations by using the inverse. Okay. All right. So what is A here? So we have a system of equations, and it's going to be the form AX equals B. And here, I'll have you fill in the blanks here. Okay, so what's A going to be? Anyone?
3, -7, -6, 13.
Good. And B will be what? Anyone?
10, 2.
Good. All right. So we have our A and our B. And so what we'll do is we'll just, ooh, where did that come from? Do you see that? Did I go wrong? I don't know. Do people see something on the screen?
Yeah.
Oh. That's interesting. Maybe I got Zoom on. Okay. Anyone else that knows? Okay, well, anyway, let's continue on. All right, so now let's use let's find the inverse for this thing. Okay, so what we have to do is we have to find the inverse. So first of all, let's calculate the determinant. So that's 3 times 13 minus, ooh, that's funny, the same one, right? Okay, so we calculated that. And again, we switched the two. And you notice that it's basically, it's exactly the same problem that we had before. Okay. We had done this before, right? In this example. Okay. So that's going to be minus 1/3, 13, 7, 6, and let's make sure that it's the same answer. 13, 7, 16. Okay, everything's good. Okay, so that's the inverse. And so when I take AX equals B, I apply A inverse to both sides. And this will should say that X is equal to A inverse on B. Okay, that's the solution. We've already seen that. So X, well, that's going to be minus 1/3, 13, 7, 6, and 3. And B is 10, 2. Okay, is everyone all right with that? That's A inverse B. And let's try to calculate this. So it's minus 1/3. So let's see. All right, so when we take the dot product, we get 130 plus 14. So it's 144. Is everyone all right with that? We're just matrix multiplying this thing with this thing over here, taking the dot product. And then we take the dot product to 6/3 with 10/2. That's going to be 60 plus 6, which is 60 plus 6 is 66. Okay, any questions on this? All right, so now what I'd like to do is I'd like to state some properties of inverses that we're going to use and which are useful. And then later on, after that, I'll actually show you a way to calculate the inverse, not just for a 2x2 matrix, but for an n-by-n matrix. So we'll do an example of a 2x2, and then we'll do an example of a 3x3 matrix. Okay. So let's look at properties. Okay. All right, so here's some basic properties. So these are kind of intuitively obvious. If you take A inverse, and I take the inverse again, what do you think I should get?
A.
Okay, good. You skip back to where you started from. Good. So 2. Now, if I take the product of the inverses, then that's going to be equal to B inverse A inverse. So what you have to do is you have to reverse B and A and take the inverse of both of those. Okay? And 3, if I take A transpose inverse, this is going to be, I can actually interchange the transpose and the inverse. So if I take A transpose inverse, it's the same as A inverse transpose. Okay, so let me just give you a justification, let's say, of one of these. They kind of go the same way. So let's look at number 2, for example. So if I take the product of A times B times B inverse A inverse. Okay. So now I associate, so this is A, B, B minus 1, A inverse, which is the same as A times identity times A inverse, which is equal to A times A inverse, which is identity. Okay. And then similarly, what you can do is you can show that B inverse A inverse is equal times AB is equal to identity also. All right, so we know that we have a matrix such that when I take the product of it times AB, I get the identity. So by uniqueness of inverses, B inverse A inverse has to be the inverse of A times B inverse. So by the uniqueness of inverses, AB inverse has to be equal to B inverse A inverse. Okay, because B inverse A inverse satisfies the property of the inverse of the matrix. Okay, so that's how these things go. Okay, any questions on this so far? Okay, so now what I want to do is I want to move on to how to define the inverse of a matrix. Okay. All right, so what we'll do is we'll actually use Gaussian elimination in a kind of more sophisticated way, right? I should say more sophisticated, but just more involved. All right. So if I look at A times A inverse, so I'm going to write this out as A times, well, I'm going to write A inverse in terms of columns. Okay, so this whole thing is A inverse. Okay. All right, so when I write this out, then this just becomes A on x1, A on x2 down the columns, A on xn. All right. But we know that A times A inverse is identity. So I have 1, 0, 0 here, 0, 1, 0, 0, 0, 0, 1. So what am I doing? Well, I want to solve for x1, x2 up to xn. So we want to find xj, j equals 1, 2 up to n, such that A times xj is equal to the vector, or it's the unit vector ej. Right? So it's a vector with ones down in the j spot and zeros everywhere else. Okay, we already know how to do this. We can just use Gaussian elimination n times. Right? So one can find the xj's by using Gaussian elimination n times. Okay, so you sort of put in a times each of the unit vectors into your Gaussian elimination machine, and you could just spit out the xj's after you kind of do this. Now, there's a more sort of systematic way to do this, but I wanted to show you that basically it does come down to Gaussian elimination, and here's what you do. Okay. So instead of just putting one of the EJs as B, we put them all in simultaneously. So what we do is we start with the matrix A here, and then you sort of draw your little fence. And instead of just putting one of the unit vectors in here, you just put the entire identity matrix. Okay? And then what we'll do is we'll just apply Gaussian elimination to everything. Okay, we're going to do row reduction. And then the idea is to transform this from A, and we're going to transform the left side into the identity. And once we transform this using Gaussian elimination, the right side will just be A inverse. Okay. So what we're going to have to do is we're going to have to row reduce to get it into upper echelon form. And then we're going to have to continue and then put the sort of the upper half into sort of lower echelon form to get it into the identity. And then we're good to go. All right, so I'll have to show you this through some examples. All right, so let me show you this via an example. All right, so find the inverse of our favorite matrix, 3 minus 7 minus 6, 13. All right. Okay, so you know the answer to this. We've done this using different approaches, but let's just make sure that I'm not sort of BSing you by this approach. Okay, so we're going to actually use this approach, and then hopefully we get the right answer. Okay. All right, so here we go. So let's put in this matrix over here. And then we put the identity matrix off to the right-hand side. All right? Okay, so we're going to use Gaussian elimination on this. So again, we want to use the 3 as a pivot here. So let's do that. So I'm going to multiply the whole first row by 2. Keep the first row the same, and then add it to the second row and put the result in the second row. So again, 2 times row 1 plus row 2, and we're going to insert this into row 2. Okay, so let's do that. Sorry, I'm going to go kind of slow on this just to make sure that we understand all the steps. So 3 minus 7. 1, 0. I get a 0 here. So I get minus 14 plus 13, that's a minus 1. And then I get 2 plus 0, that's going to be 2. And then I get 2 times 0 plus 1, and that's a 1. Okay, is everyone all right with that? So far? Yes. so that's the process, right? We're going to start with A and then the identity matrix on the right-hand side. We're going to transform the left-hand side into the identity, and then the right-hand side will turn into the index. Okay? So here, let me just write this in. Actually, let me just, I'm trying to do this. So this part is A here, okay? And this part is identity. Okay, any other questions? All right, so now what we have to do is, this is already an upper triangular form, and now what we want to do is, we eventually want to divide the rows by certain numbers, okay? But let's not do that yet, otherwise we're going to work with a lot of fractions. Okay, so the next thing we want to do is we want to use this bottom thing as a pivot, and we want to knock out this 7 up here. Okay, so what I'm going to do is I'm going to multiply this row by -7. Okay, so let me write out this thing. So I'm going to multiply -7 times row 2. I'm going to add it to row 1, and then I'm going to insert it into row 1. Okay, so let's do that. Okay, so I have 0, -1, 2, 1 still. And what do we get? We get 0 times -7 plus 3, that's going to be 3. The next one we get is 0. Then I get -14 plus 1, that's -13. Okay. And then I get -7. Okay. Now I'm not sure I think 7 or -7. I guess I have -7. Oh yeah. Okay. All right. Okay, so now we have this, right? And so so what do we get next? Well, so is everyone all right with this step so far? Okay, so now what I want to do is I want to actually divide by 3. So I now want to divide row 1 by 3. Okay. So I get 1, 0, -13 over 3, -7 over 3. Okay, and now I want to multiply the bottom one by -1. So I'm going to divide row 2 by -1. And I get 0, 1, -2, -1. Okay. Now let's see. Am I missing? Okay, so let's check the answer. Yeah. Okay, so let me check the answer. Okay, so in the answer I get this. I get -13 over 3, -7 over 3. Yeah. -13 over 3, -7 over 3, that's correct, right? Sorry, I have to scroll up here. So let's kind of look at this answer over here. So -13 over 3, -7 over 3, that's okay, right? And then I should have -2, -1. Okay, so we go down here, minus 2, minus 1. Okay, so this checks out. So this is, let me just write this in. Okay. So this one's the identity over here. And this one's the inverse. Okay, any questions on this? How we did this? Oh, I divided. So what I did was I took this matrix up here. Or this matrix up here. Right? And I took the first row and I divided it by 3.
I meant like this and that.
Oh, so if you go up to the first part, here. So remember, minus 1/3 times the whole thing. Okay. So it's minus 13
Yeah.
over 3. Does that make sense now?
Yeah.
Okay, so you have to multiply the whole thing. Okay. All right, other questions?
So in general, is our goal with this to turn the left side into the identity matrix, just to say it simply?
Yes. So the idea is you set it up like this. Oops, sorry, I went too far. All right, so you set it up where you have A on the left side and identity on the right side. You use Gaussian elimination to transform A into the identity, and then out on the right-hand side, you'll spit out the inverse.
Okay, makes sense. Thank you.
Okay?
Can you explain one more time how I guess J correlates to n times, or why it takes n times to solve for EJ?
Sorry, which part are you?
Up above where you write out that
Yeah,
J matrix.
y A times.
Or yeah, one can find xj by Gaussian elimination n times.
Yeah,
Can you explain that again?
well, I mean, you have a system that you have n systems of equations. Namely, A times xj is equal to EJ. And you want to find the xj's. And how many of them are there? There are n of them. So what I'm saying is that if you want, you could sort of solve for each xj and do it n times. Or you can actually do it the way that I did it, where we sort of do it all simultaneously. That's the point. Okay? So instead of just having one column, this is a good point. So instead of having one column or one vector in for B, we have n vectors, namely with the identity matrix. And then we just sort of do it all at once.
Okay.
Does that make sense?
Yeah.
But what I wanted to do was I wanted to actually, if you want to use your deconstruct, I wanted to deconstruct the process to sort of indicate that it's just Gaussian elimination.
So this solves it in a quicker amount of time then?
Yeah, I mean, just in terms of bookkeeping, yes.
Okay.
Oh, well, you would just take, if you want, you would take, all right, so if you want to do the other way, you would take this matrix over here, 3 minus 7 minus 6, 13, and then you would just put 1, 0 in first, and then you would do 3 minus 7 minus 6, 13, and then you put in 0, 1. Okay, and so when you're solving for this part down here, okay. So like I said, we're doing it all at once. Okay, good. All right. Okay, so I want to save the next example for the class next time because I want to short people out. So what I'll do is I'll state something or state some ideas before the end of class. Okay, so we will find the inverse of 3x3 matrix on Wednesday. Okay, I don't want to short the example, namely, I don't want to have to rush through it. So what I'll do is we'll just do that on Wednesday, and then let me, for the remainder of time, just kind of give you some ideas using this Gaussian elimination process. Okay, so there's the following theorem. And so from this process, you can kind of figure out when a matrix is invertible or not. So it's basically invertible if I have all the pivots. If I'm missing pivots, I'll never be able to turn this A into the identity using Gaussian elimination. So that's basically what this theorem is saying. So the following are equivalent. Okay. So let A be an n by n matrix. Okay, so here's the following statement. So the first statement is A is invertible. Okay, so A has n pivots. Okay, so this process actually tells you when a matrix is invertible, you need n pivots in this Gaussian elimination process. So if you have n pivots, then the homogeneous solution is trivial. Okay. So I guess that's also clear if A is invertible because you can just apply A inverse to both sides. Right? Now, as we saw, if AX equals 0 has only the trivial solution, that means the linear transformation from Rn to Rn is 1 to 1. Okay. Equivalently, the columns of A are, okay, someone fill in the blank.
Linear combinations.
Almost. Are they dependent or independent?
Independent.
Yeah. Good. Linearly independent. Remember, when you're showing that AX equals 0 only has a trivial solution, you're basically showing that the columns of A are linearly independent. Okay. So this theorem actually sort of takes all these various ideas that we've been working with and sort of puts them all under one umbrella. Okay. 6, AX equals B has a unique solution. Okay, we've seen this before. If A is invertible, and then if we have a solution, then when I take the linear transformation from AN to Rn to Rn, this is onto Rn. Because if I take a B, I know there are X's such that I can write the combinations. I can take the columns of A and sort of write it as a linear combination of B. Okay. Or sorry, I can write B as a linear combination of the columns of A. So that means that A is onto. Okay. 8. The columns of A blank Rn. Okay, someone fill in the blank.
Span.
span. There we go. Okay. Because, you know, if I take a B over here, I can actually find the x's such that B is a linear combination of the columns of A, so therefore the columns of A will span R. Okay. Any questions on this? So this is kind of a summary of all the various concepts that we've done in terms of linear independence, spanning, invertibility, systems of equations, sort of all under this one umbrella. Okay? So it's a lot to contemplate, but you know, I urge you to go home and kind of think about this theorem just for a little bit. Okay, so we will stop here at this point, and we'll continue on with some more examples next time. And then I will actually relate this to linear transformations, and we'll do some problems involving linear transformations. Okay. And Friday, we'll probably start in on a review for the midterm. Okay, any questions? Okay, so we will see you on Wednesday.
Thank you.
Thank you.
Thank you.
Thanks.